Okay, we have an interesting problem here from MIT 2019, number 12. We need to find the limit as n is approaching infinity of the integral from minus infinity to infinity, e to the minus x to the 2n dx. Okay, it's kind of troubling at first just because of the limit, because if you kind of just wanted to like jump to the end and think about plugging in infinity here, now you're going to have infinity in the exponent. It seems like as n's going to infinity, this thing's going to zero pretty fast. I wanted to at first just put down zero, but we also have to consider what our x values are. One thing we can do on this is we know that this is an even function because we're going to have an even exponent here. So what we can do is use the property of even functions on this, change this bound here to a 0 and bring a 2 out front. But actually you can bring a constant outside of the limit too, so we can actually bring the 2 all the way out here so it doesn't bother us. And now from here, I think we need to get into the behavior of this limit. We can look at what's going to happen with x to n, but we should break this up into two cases. Our bound's going from 0 to infinity. Let's first look when, let's say our x is between 0 and 1. We're not too worried about like at 0 and at 1 because it's going to be an integral, so those are going to be insignificant. But if we look at the limit as n's approaching infinity, not the whole thing, let's just look at x to the 2n. Well, when x values are between 0 and 1, raise it to a large power, this is going to be going off to 0. So then using this, let's look at the whole expression. If we look at the limit as n's going to infinity of e to the minus x to the 2n, we already determined this part is going to be going to 0. So basically e to the 0, this limit's just going to be 1. And then we can do the same kind of thing, looking at the limit for values when x is greater than 1, going all the way to infinity. What's going to happen? We want to look at the limit as n is going to infinity. Same thing, x to the 2n. Well, for x values greater than 1, we've raised it to an infinite power. This is just going to blow up, and this limit's going to infinity. So then doing the same thing as this part over here, for this limit, for e minus x to n. Now, this is going to infinity. Sorry, that kind of messed that up. But this part's going to infinity here, and we have a minus sign on it. If you want, you can look at it like 1 over e to the infinity. Well, then that part's just going to 0. So this right here is going to give us an approach because we can break up our integral the way we've broken up the bounds right here. We'll do two integrals, one going from 0 to 1, one going from 1 to infinity. And we basically know it's a limit, right? But we basically know what the value inside the integral is going to be. So let me clean this up and let's see what happens when we break this into two integrals. Okay, now breaking it up this way from what we found on the previous board, we basically know what these values are in here. Like with this limit, if we could bring the limit inside this limit right here, we found this to be 1. And here, if we can bring this limit inside, we found this limit to be 0. Now, the funny thing about this one is it actually would be pretty easy to do this in the integration bee because in the integration bee, they don't check your work. So this is going away because this is basically 0. We can consider this 1, integrate 1, and then we're done in like 2 seconds. The only thing is I'm not doing an integration bee right now. I'm doing a video on YouTube. And so for that, I need some more justification in order to bring the limit inside the integral, bring the limit inside the integral. So what we actually need for this is the dominated convergence theorem. We need for each of these, we have two functions here, even though they're the same thing, they're different because of the bounds we're working with. We need to bound these each with some integrable function. So starting with this one over here, let's call this our f of x. So what we're going to need for this is we're going to need the absolute value of f of x to be less than or equal to g of x, where this is going to be some function that we already know we can integrate. And this has to hold true for all x and all n greater than or equal to 1. Well, I'm not going to worry too much about absolute value on the exponential because it's always going to be positive. But what I want to notice on this, I'm saying for what's going to happen is what we can use on this is e minus x to the 2n. I claim this is going to be less than or equal to just e minus x. And if you think about this, when n values start at 1, we're going to have at least e minus x squared. As the exponent increases, these values are just going to be less and less. So this is always going to be less than e minus x, especially, and it's also important to notice because our bounds were between 1 and infinity, we don't have to worry about this case. So this here is true. And so that's going to allow me to bring the limit inside the integral, take the limit here. This is going to be 0. We're just integrating 0, so this piece goes away. And then let's do the same kind of thing on this one. For e to the minus x to the 2n, this is gonna be like our f of x over here. Again, not worrying about absolute value, but that's always gonna be positive. Let's write it this way. Let's write it like 1 over e to the x to the 2n. And maybe, I should actually split up a little different. Let's write it as e to the x squared to the n. Not that it really matters, but let's just do it that way. If we think of our x values between 0 and 1, maybe let's just use an example on this to make it clear. If x is 1/2, then you square it, that's going to be a 1/4. We're going to be looking at something like, this is going to be like e to the 1/4 to the n. Like, look at something like this. Well, we're saying our n values are going to be greater than or equal to 1. So you're going to be getting something at least e to the 1/4, e to the 1/10, e to the 1/20th. You're going to have, think of it like this. You're going to have e to some large root here, a relatively large root. What's going to happen on this is when you take larger and larger roots on e, which is something like 2.718, this is going to be going to 1, but never quite reaching 1. So what's going to happen is this here is always going to be less than or equal to 1 because this is never going to quite reach 1. So for g of x, we can actually use 1. We know we can integrate that, and that's going to converge, especially from 0 to 1. So this check works here as well. So what we can do is get rid of this second one, clean this up, and then we can just bring our limit inside the integral on the second one. Okay, so now that we have it written this way, we've already determined this limit, which we found earlier. This limit here was just going to be 1. So we're just integrating 1. Doing this out, we have our 2 in front, integrating 1. This is going to be x, just evaluated from 0 to 1. Plugging in, this is going to be nothing. Plug in 1, and for my final solution to this, we just get 2. Okay, so again, if you're actually doing an integration bee or you plan on competing in an integration bee, don't do all this stuff I did here. Just go ahead and plug in the limit and just put down the answer. You could even guess. But on the other hand, if you're just at home doing the problem, you should probably do the check and make sure this is really legitimate. Okay, that's it for today. Thanks everyone for watching. Have a good day.